But you might ask, how could Mount Everest be flooded? There's not enough water on the earth to flood Mount Everest. And you're absolutely right, because the Bible tells us that the mountains formed rapidly at the end of the flood. But then another question arises. Wouldn't that generate a lot of heat from this process of friction? And yes, it would, but this is fine. How else would 90% of all the aquatic life die in a global flood? So yes, there was a lot of heat generated, but it's not a problem. The two most popular flood models of today both generate a lot of heat, but both from different processes. You see, catastrophic plate tectonics generates the heat from accelerated nuclear decay, and the hydroplate theory from the production of radioactive elements. These are both easily resolved by just removing two assumptions from each model. Walt Brown, who created the hydroplate theory, believed that God did not create radioactive elements before the flood, so all of the heat generated in his model came from the creation of super heavy elements which rapidly decayed into radioactive elements. Remove that assumption and you no longer have that problem of heat. In the catastrophic plate tectonics, they try to alter current radiochemical dating by saying that nuclear decay of those elements sped up during the flood. This creates massive amounts of heat, and there is simply no reason to invoke this. The radioactive elements were simply moved around and reshuffled with all of the other elements during the flood. They were neither created during this event, nor went through accelerated nuclear decay at this event. Now, the heat is only generated from friction, which heated the oceans, and much of this heat was put into the atmosphere itself.
And take a look at this statement. A sudden exposure of the mantle to 70% of the Earth's surface would release enough heat energy to boil the oceans dry several times. This is comparable to the statement, your oven has enough energy to set your curtains on fire. They are not on fire, so you don't have an oven. For comparison, the Tsar Bomba released more energy than all weapons and bombs in all wars combined, yet nobody got killed. So two things are important. It's not only the amount of energy that is involved that matters, but also the heat transport. In other words, where is the heat? So heat transport then. How do we get heat from here to there? Basically, there are only three ways to do that: heat flow, conduction, and thermal radiation. It's possible to trap heat, like heat, inside the Earth. Let's take a random example. Assume we have a large piece of rock and suddenly parts of this rock gets molten for some reason. It expands a little, and now let's add water to it. And let's assume the rock contains enough heat to boil all this water away. So the water then starts to boil at some point, and the lava is starting to cool down. The lava sinks slowly, causing some places where hot rock goes upward. And after a while a solid layer forms on top of this molten rock, and then eventually we would have a situation where a solid layer isolates the hot molten rock from the water. So we'd end up with trapped heat and still a lot of water on top. So for all the oceans to evaporate, all heat must end up in the ocean, which does not happen. So let's take a look at what would happen if continents shift quickly, exposing hot mantle material. Say the left is South America, the middle part is lava, but this is what is going to be the Atlantic Ocean, and the right is Africa. The lava is lighter than the solid rock, so it expands. Not only does this boil the ocean away there, but it also pushes the ocean away there because of the expansion. The result is that it would start to rain like crazy in colder areas, and that is on the continents. So we would have a situation where the ocean is flooding the continents, and the lava has a lot of freedom to expose its heat to the sky and the universe. At the edge of the continents, the water touches the hot lava, enhancing the solidification process there. Because it solidifies, it shrinks and becomes denser than the continents, so it leaves more room for the water there. The molten lava is being squeezed out horizontally and wants to flow on top of the solidified lava. But there's water there, so it also starts to solidify. So the water is slowly pushing the molten lava towards the middle, and eventually two layers of solidified lava lean on each other, and this causes a closing seam, a closing midpoint, which we identify today as a mid-oceanic ridge. When the crust is solidified, it's still quite hot, about 1000 degrees Celsius. Then conduction takes over for the cooling down process. We can also calculate this. We have a formula that says that heat conduction per time is the thermal conductivity times the area times the temperature difference on both sides of the material divided by the thickness of the layer. To do this properly, we must divide the materials up in smaller layers, because each of these layers have their own temperature, and thus they have their own amount of heat energy and their own conduction speed. All these layers give their energy to their neighbors, and only the top layers releases that energy to cool the whole lot down. So we start with a lot of layers that are 1000 degrees Celsius each, except for the top layer, which is at room temperature. Remember, there's water on top, which consumes a lot of heat. The layers are 50 meters thick each, and we're using a time interval of about 100 days to calculate the conductivity step by step. And we represent the temperature with colors. Red is 1000 degrees Celsius, yellow is 500 and green is 20. Here we display a layer of 7 kilometers thick. This is what it looks like after 90 years, 1000 years, 2000 years, 3000 years, 4000 years, and let's stop at 4500 years. If we are looking at the Genesis flood, it could be that this is close to the time that has passed since. There are uncertainties at when the flood year was, which is a subject for another discussion, but let's just see what the result is after 4500 years. In this scenario, all would have cooled down and we would find the maximum of 590 degrees Celsius at 4700 meters depth. Remember, we still have a lot of volcanic areas, which are in the basaltic oceanic crust, so conductivity is happening there. Since these are still hot today and only a few kilometers depth, it means these volcanic areas could not be millions of years old. This calculation shows that it can only stay hot for thousands of years. Now when it comes to heat, there are some pretty weird phenomena that come into play. One is a thermocline. You may wonder how fish could survive such a scenario. Let's say we have regions with hot water and regions with cold water. Then there are also places where the hot water flows on top of the cold water. And the hot water kills the fishes. Yes, we find a lot of dead fish in the geologic layers. And the fishes in the cold water can survive. The hot water is less dense than the cold water. This causes that hot and cold water don't mix very well. This causes a separation between hot and cold water layers, and this separation is called a thermocline. Important for fishes, but you don't need that information for the rest of this presentation. Now the next issue is power law creep. Power law creep is a process that causes rock to become viscous without increase in temperature. How do you do that? Well, let's assume we have several layers of rock, we put pressure on it, and we are going to push the top layer sideways. That is called shear stress. Then the middle layer will start to deform. In other words, it changes shape. Now if you put a gigantic shear stress on the top layer, the layer below dramatically changes shape. This process is very strongly non-linear and has to do with molecular structures breaking up and crystalline surfaces sliding on top of each other. It is very complex, but it has been tested in the laboratory. You can compare this with toothpaste. Toothpaste is solid until you put pressure on it, then it changes shape, but it will become solid again as soon as the pressure stops. This process reduces the viscosity of the rock up to 14 orders of magnitude, and thus it's very strongly non-linear. In very extreme conditions, solid rock can flow like water, without increase in temperature. The last weird phenomenon I'm going to show you is the crossover depth. We are used to magma rising up because molten material has a lower density than the same material in solid state. But it appears that molten rock is better compressible than solid rock. So if you put a lot of pressure on lava, it will eventually become more dense than the solid rock. So magma that is very deep inside the earth sinks. The point where this switches from rising to sinking is called the crossover depth. Depending on the rock type, the point where this happens is between 200 and 400 kilometers. This phenomenon has also been confirmed by multiple laboratory experiments. And very importantly, it shows that magma cannot come from deeper than 400 kilometers. The crossover depth is about here.
This rapid subduction was the main source of heat during the flood, in my opinion. But how can we say that this happened? Well, we have evidence that this happened, and happened fast, by looking at P-wave cross-section mantle tomography images. They show cold plates of Earth's crust that have been subducted into Earth's core. This must have occurred recently and rapidly, and is the only way they could be where they are, near the hot molten core of the Earth, yet still have a cooler temperature from the surrounding rock. So, with fast mutation rates, low genetic diversity, independent lines of ancestry with genetic borders, and biological evidence of a global bottleneck inside of all life, with cold subducted slabs of Earth's crust near the core, with visual evidence that animals have no problem inbreeding to repopulate, and rapid speciation rates, especially in an empty world following a catastrophe, all of this points to one conclusion: the young Earth creation biblical model of ancestry.